Hi, this is a different video from what I normally post, but consider a Christmas slash holiday special for me. Today we're going to be talking about an interesting holiday math problem that I thought was cool, so without further delay, let's begin. So, for some context, every year at my high school, on the day before break, there is a holiday assembly in which winners of various holiday-themed competitions that were held throughout the month of December are announced, and they call down some people to play some holiday games in which each grade competes against each other. It's a pretty fun time. I won't go into full story time here and list everything that they did, but one of the games was kind of interesting, at least from a mathematical perspective. The game was called Light Up the Christmas Tree, or Light Up the Christmas Lights, or something like that. I don't exactly recall. However, the basic idea was that from each grade, 3 people would be called down and each team would have 6 Christmas lights. In this case, they were cones that were all off, standing. Each cone would have a number, and you would roll a die, and if you got the number of a cone, you knocked it down if it was standing, and in this case, that would be turning the light on. But if it was down, you would have to put it back up. In this case, you would have to turn the light off. So essentially, you're toggling the lights. The first grade to knock down all of their cones or turn on all of their lights will win the game. Don't ask me why we need 3 people to roll a die and knock down cones, but I didn't make the rules. Now, of course, being kind of a math nerd, the first thought that I had when hearing the rules for the game was, what's the expected value or average number of rolls that we need to win the game? I then asked this question out loud to my other nerd friends, and 2 of my programmer friends had the immediate thought of writing a simulation on their school Chromebook to get an estimate, which I thought was funny. I consider myself a computer nerd as well, so I quickly followed. Anyway, here's a rough historical recreation of the code that I wrote. I got a value close to 83, and a friend got a similar answer as well, so we were pretty confident we were in the right ballpark. I wrote the simulation in Python, and my friend wrote his simulation in Rust and ran it over 100 million games and got value in the range of 83.15-ish to 83.2-ish. So yeah, that's it, right? The value is about 83 and we're done. As for the game, it turns out that 83 dice rolls is quite a bit, and the students running the assembly had to kind of intervene, and I believe the juniors eventually won. So yeah, everybody can go home and now enjoy their winter break, right? Wrong! While engineers might be happy with approximations, I'm a man of mathematics and I do not believe pi is equal to 3. We are going to calculate the exact value! The main obstacle to overcome when calculating the expected value is figuring out how to deal with the fact that if you get really unlucky, the game can go on forever. However, we do have a finite number of states the lights could be in, 2 to the 6 or 64 to be exact, and from each of these states we can get to one of 6 other states with 1/6 probability. We therefore can write the expected value of the number of rolls for each state as an equation of the following form. The 1 is added because we have to roll the die at least once to get to another state. Therefore, we can create a system of equations with 63 equations. Of course, the state with all the lights on just has value 0 because we're already at the winning state. Now we just need to solve 63 equations, and we can then get our answer. Of course, I'm not that crazy. We can have the computer do it for us. We can rewrite the equation as the following. And then for each equation, we can have a vector of values representing the expected values of each state, call it E, and then put all of the coefficients in a matrix M. This is just basic linear algebra, and we can then have this matrix vector product equal to a vector V that has all components equal to -1. I just wrote a Python script to solve this matrix equation using NumPy, and it spat out a value approximately equal to 83.2. And I imagine the only reason it shows some weird decimal parts is due to floating point imprecision. Some other interesting facts to know. The expected value for when you have all the cones knocked down except for 1 is 63, which is quite a bit and a little intuitive, but the math does work out. Additionally, the probability of winning instantly after 6 dice rolls is about 1.54%, which isn't impossible if you think about it. It turns out all the states are symmetric based on how many lights are on, so we just need 6 variables and 6 equations. Equation and variable for each expected value for the number of cones or lights that are on, which is not that difficult to solve by hand if you want to put in the time. I'll save you the math and just write the exact expected values. It does turn out that the expected value is indeed 83.2, and we are finally done. Anyway, that was a nice problem the assembly gave me. I suppose that counts as my Christmas gift this year or something. Anyway, I hope you guys enjoyed this brief look at this problem along with a little bit of story time. If you want more of this kind of video, consider commenting below with any feedback. Have a Merry Christmas, Happy Hanukkah, Kwanzaa, whatever holiday you celebrate this time of year. Hey, who are you?
Where are all the cones that got kicked when making this video?
Wait, what? That was for science! I had to run the simulation to get an estimate first!
Well, this This time we are defenseless, and we're sick of your oppression. The revolution has begun. Get 'em, boys!
Well, I guess that's my cue to leave. Ah! Ah! Ow! 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 I can't!